Okay, so we need the standard enthalpy of dehydration of the hydrate. So the reaction for this that we're interested in is CaCl2 dot 2H2O solid yields CaCl2 solid plus 2H2O. Okay, liquid. Not, yeah. All right. So we have enough information at this point to calculate that because we now have, we can use Hess's law. All right. So let's see how we can do that. I want the standard enthalpy of dehydration of the hydrate, which is this reaction right here. Calcium chloride. So let me write those down for you. So we know calcium chloride solid yields calcium ions, aqueous, plus 2 chloride ions, aqueous. We know the delta H for this, right? We've calculated that. That's what we just calculated. And our experiment, so this is from literature data. From our experiment, what did we do? We did calcium chloride dihydrate. Solid, right? And we dissolved it. We got calcium chloride aqueous plus 2 chloride aqueous plus 2H2O liquid. We know this one from experiment, correct? So we can combine these two. We want the delta H for the dehydration of calcium chloride dihydrate. So you want a reaction where calcium chloride dot 2H2O solid ends up without its water of hydration, but it's still a solid plus 2H2O liquid. My intention here is for you to be able to apply Hess's law. Can you combine these two equations? Let's call this equation 1 and equation 2 to get this overall equation, which is the dehydration of calcium chloride dihydrate. What do you do? I want calcium chloride solid on the right. So what do I do with equation 1? Okay. Flip it. So we need to flip this. And then what do I do with the second one? So let's go ahead and flip that. Calcium chloride aqueous plus 2 chloride aqueous yields calcium chloride solid. So delta H for this, we know is the opposite of the other one, right? So what do you do with the second one? As is. So when you add this and this, what do you get? Calcium chloride solid cancels out, right? No, you have that. You keep that product right there, sorry. Calcium chloride dihydrate stays. What cancels out? Calcium ion cancels out. Chloride ion cancels out. And we have the overall reaction. Correct? So what we have here is the delta H for the dehydration is equal to the delta H experiment, which is the dissolution, right? Minus, you flip the other one, minus the delta H of the dissolution of the anhydrous. This is the dissolution of the hydrate. The second one, okay, minus the dissolution of the anhydrous compound, right? So what's our formula here? This is the dissolution of the hydrate, which is this number right here, minus delta H for the dissolution of the anhydrous. So it's 45.5. So do we expect, is it reasonable for the dehydration of a hydrate to remove the water of hydration to be endothermic? Yeah, it's a decomposition reaction. In fact, one of our traditional freshman chemistry experiment is you have a hydrate, you heat it up, you remove the water of hydration. It's an endothermic process. All right. So that was the purpose of that step, for you to be able to apply Hess's law. Okay. So for your unknown in the lab, you should be able to calculate the enthalpy of dehydration of the hydrate in your lab that you did in the lab. All right, what else can we calculate? We can calculate the delta H of formation of the hydrate. What would be this reaction? This would be elements in your standard state, right? Giving you what? The hydrate. 1 mole of hydrate. So how would you calculate that number? Let's take a look at our dehydration reaction again. We can use this reaction right here, right? The dissolution reaction that we have. So we have calcium, and let me make this red. Calcium chloride dihydrate, solid, gives you calcium ions plus 2 chloride ions, aqueous, plus 2 H2O liquid. We know the delta H for this from experiment, correct? That's what we did in the lab. You dissolve your hydrate in water. Do you know the delta H formation of water? We know that. We can look that up. Chloride, we look that up. Calcium, we look that up. So we just need to know what this is, right? But that's actually what we want. So delta H experiment is equal to 1 times the delta H formation of calcium ions plus 2 times the delta H formation of chloride ions, 2 moles times the value per mole, plus 2 times the delta H formation of water, liquid water, minus delta H formation of your hydrate. And all you have to do is switch these two. This one goes here, and then this one goes there, right? So let's calculate the delta H formation of our hydrate. Delta H formation of our hydrate is going to be equal to, well, what's our formula? Formation of chloride and water, and calcium, so it's equal to 1 moles of cation times delta H formation per mole of cation. You still with me? Plus moles of anion times the delta H formation per mole of the anion. Correct? Plus delta H formation of water, 2 times the delta H formation of water per mole, minus your experimental delta H, which is this number up here, which we got earlier. Delta H for the dissolution of the hydrate. So this one uses delta H of formations. If you press enter, it's minus 1412. That's the standard enthalpy of formation of your hydrate. So it's not easy to find the standard enthalpy of formation of hydrates, but I found a source, and that's Lang's handbook. So I need you to look at Lang's handbook, look it up for me. Let me pause this recording. All right, so the number from Lang's handbook is negative 1402.9. Okay, so this is Lang's handbook, 14th edition. What page number is that?
I thought it was 6 H2O.
That's hexahydrate. We want the dihydrate. Page 6.74. Okay. So how do you calculate? What's your percent error then? Our experimental value is 1412.9 minus the literature value of 1402 divided by the experiment literature value times 100%, 0.79% error. Okay. So you're going to do the same thing for your sodium acetate trihydrate or whatever unknown I assigned you to.
Or anything from the website for this last one?
Just take a picture of the handbook. Okay.